series and parallel circuits, lesson 33. So we will be able to compare series and parallel circuits. Now, we've already talked about what a series circuit and a parallel circuit is, but I guess we haven't really talked about how their differences are, what are the advantages of one, what are the disadvantages of the other. This is going to be useful because later on we're going to talk about, which ones we use in circuits. Do we use the resistors, or do we use series, or do we use parallel? So let's jump back in time and see what we did last lesson. Last lesson, what we did was we did a lot. I talked to you guys for pretty much an hour straight. What we did was we just created circuits. So we started off by exploring, we started off by coming up with this law for a series circuit. This is going to be our resistance rule. And our resistance rule is going to be like, essentially, we can turn three little resistors in series into one big resistor, because essentially you're just creating more work for the electrons to go through. So instead of creating three little hurdles, let's just make one big hurdle that's going to have them struggle with it. And so that gives us these three laws for series. After that, we jumped in, we did some calculations, and then after we did some calculations, we actually went and we looked at some circuits. We did one circuit where the two resistors were the same, one circuit where the two resistors were different, and then one circuit where we had a current, but we didn't know the EMF. We didn't know the voltage of the battery. So we had to do the same thing that we just did in that previous example, where we had to find the total resistance and the total current. This one was a bit easier though, because the total resistance is just 7. Sorry, the total resistance is just 7 ohms, and the total current was 0.4. So that meant getting the total voltage was pretty easy. We then spent some time talking about parallel resistors. Parallel is a bit different. The total resistance of a parallel circuit is linked to the sum of the reciprocals. And I said that, so that means that if you have 3 12-ohm resistors, it's the same as saying having one 3-ohm resistor. So I thought it was a bit different. It shows that even though, and the sort of analogy for that comes from this pump here. If you have one thin resistor, it's going to slow down the flow. If you have 2 thin resistors, yes, it's still going to be difficult for the current to go through, but essentially what you're doing is just creating more paths, more ways for the water to go through. So therefore, it's going to mean that there's going to be less resistance overall. Kind of like, I don't know, whenever I keep talking about this, I keep thinking about shower heads. I keep thinking about, if you go to have a shower and it's got lots of little holes, and you can think about it, it's like, wow, there's a lot of water coming out of the shower head, but it goes through small holes. It's like each of these holes is like a different rail in a circuit, in a parallel circuit for a battery. Each of them gives a different way for the water to escape the shower head, and that's why we end up with, being able to have showers, because there's just so many ways for that current to go through. That's just how I always think about it lately. I'm not sure if that analogy may not help, but I don't know, it sort of makes sense to me. We then looked at these. This is our first comparison, I guess. We looked at how does the current compare, the voltage, and the resistance. How do these three all compare? We did a quick little question here, and then we did 3 more examples. Actually, we did 2 examples. We did not finish this. We did not do the last example. So my first thing that I'm going to do today is going to crack open this last example, get that done, and then we'll move on to some of the other comparisons we can make between these 2 types of circuits. So let's grab this guy a try. First up, what should we work on first? What do you think what do you guys, I'm going to open up chat here. What should we figure out first for the circuit? What would be good? Can someone give me a suggestion? Voltage. Yeah, I would do voltage too, Calvin. Let's look at voltage. Now, in this case, the voltage here, let's label this A and B. The VA, we have no, well, we do. We know because it's a parallel circuit, it's going to be the same as the total voltage. So VA is 8 volts. VB, well, guess what? It's also going to be 8 volts. VT is 8 volts. And if there was more, if there was another, like, you know, part of the circuit here, then it would also be 8 volts. It doesn't matter how many. I always use 2 examples here, but I don't want you guys to start thinking like, oh, all examples are just going to have 2 resistors. You can have as many resistors as you want. So now, after voltage, the next easy one might be resistance. R1 or RA equals 2. B, we have no idea what it is. It's X, okay? And RT, well, we can't calculate that either because we don't know what X is, so we're just going to leave it. Last one, current. Now, IA, we don't know what IA is. IB, we don't know what IB is. IT, we do know. That's 5 amps. And then that's all the information we can draw from the circuit straight away. So the next part is going to be, you know, using our information that we do have to work out information that's not given. Can someone give me a suggestion on maybe what could I calculate next? What could I figure out now? What do you mean current? We've already done current. We've already done the green one. Specifically, what could I measure now? By the way, everyone, if you're not the effective resistance, well, good answer, but no, you can't actually unmute.
Imagine dropping physics for specialists, dude. You're insane.
All right, so I want to know what current of A. Good job, Leon. Yeah, all right. Anyway.
Oh my god. Yo! Who's that? Who was that?
Anyway, the current through A, we can work this guy out. We circle all of these.
It's Cameron.
We circle all these.
Cameron.
Guys.
Cameron.
Hold on a sec. Now I'm going to mute everyone again. All right. I don't want to hear about Cameron. Right. If we circle all those, we can work out IA. Thank you. I don't know who said that, but it's gone now. So we can calculate IA quite easily by doing V equals IR. A. We want to know I, so VA divided by RA is going to give us IA. And then once we know what IA is, well, once we know that VA is 8, RA is 2, we can work out IA is going to be 4. So that's going to be our answer up here, 4 amps. Okay, now I'm going to unmute everyone. Can you guys give me a suggestion? What should I do now? What's something I could do now to figure this out?
Use 5A as the total current, and then you take 5 minus 4. You find the first current is gonna be 1.
Yeah, good answer, Calvin. We can work out what the current through this is. Because we know Kirchhoff's law is going to tell us that the current, if this is 4 amps going down and this is 5 amps coming out, then this must be 1 amp going up. This is using Kirchhoff's law to fill this in. But yeah, we know two things of this circuit, so we can work out the third one. Okay, so what's next?
Find the resistance of B.
Find the resistance of B. Thank you, Daniel. Yeah, we can do that. That's pretty easy there. Same idea here. VB divided by IB is going to give us RB, which means that we're going to have V, which is 8 divided by IB, which is 1, which is going to give us 8 ohms. Great, cool. And then we've got two choices in how we find, we've got two choices for how we find the total resistance. We can find the effective resistance by either going 1/2 plus 1/8, or we can find it by going across. It doesn't matter which way you want to do it. They will both work. I'm going to use this one because I'm lazy. VT divided by IT is going to give us RT, which means that the VT is 8 divided by 5. 8 divided by 5 is going to give us, I think, 0.4, but let me just check if I made this mistake before. It's not, it's 1.6 ohms. And that's going to be our final answer here, 1.6 ohms. And so that's everything that we can work out for a particular circuit here. So yeah, that's now going to re-mute people, so don't stress if you can't say anything. That's how you would find a particular resistance for a parallel circuit. Now, when you don't know everything, and again, even though we don't know everything, it's the same process. So I don't actually see it as being that difficult. We're still finding the voltages, finding the resistances. We're looking for things that we do know to work out things that we don't know. If we know the total current, that's useful because we can use that total current to work out the individual resistance. By the way, and I would not advise doing this, but you could take 1 on RT. In this case, we knew it was 1 divided by 1.6. You could use that to find out if we knew this was 1 on 2 plus 1 on X. You could use that to find out X, but it would be, you know, a little bit difficult. You're going to have to deal with partial. You're going to have to expand it, and it's just going to be that. You could do it. I'm not saying you can't, but I'm just saying that would be difficult for me. Yeah, you could find the effective resistance. Yeah, sorry. You could find the total resistance at the start. Yeah, sorry. Someone just suggested to me you could have found this quite easily at the start because we already knew this one and this one. I didn't think that was useful because once we worked out this, it's going to be very difficult for us to work out this 8 ohms because you're going to have to do something like this. 1 over 1.6 is going to become 8 over 5. You know, so that's, I mean, you would get 8 over 5 because a half plus a, you just have to make a common factor, and it's just going to be, you know, x over plus 2 over 2x, and then that equals, cross multiply that. Yeah, you'll get the answer, but it's just going to be a pain. Let's look at one more thing before I change topics to today's, more looking at what today we're looking at. This guy here. So in this question, we've got a mixture of both. This is not actually on the test, so I'm not actually going to assess you guys on it. I looked because I wanted to make sure that you guys did need to know this. I think you'll need to know stuff like this for year 12 physics, for year 11 physics. We just want you to be really, really efficient. But this is a mixture of both because you can have a look at this. You can see that overall, this is a parallel circuit. If you can't see that overall, it's a parallel circuit. So we could treat this as a parallel circuit. You know, how would you treat this as a parallel circuit? Well, we know if 12 volts has to get dropped over this section of the wire, And 12 volts has to get dropped over this section of the wire, just like using Kirchhoff's rule. The only difference is that this 12 volts gets dropped over this resistor. So if I was to look at this, if I was to call this resistor A, then that would be pretty easy to work out that, you know, V of A is going to be 12 volts. We know that R of A is going to be 2 ohms. And we know that I of A is going to be, you know, V equals IR, V divided by R equals I. So therefore, 12 divided by 2 is 6. We know that 6 amps goes through that top row here. But this bottom part here has got 2 small resistors. This section here is actually a series circuit because it's got one and the other. I could actually refer to this as B1 and B2. And you could still work out that, okay, we could do something separate here. So the total resistance of B, RB, the total resistance of B is going to be 4 ohms. I can add those individually and I can just treat this like one big 4 ohm resistor. So I know 12 volts needs to get dropped over the whole of RB. And I know that, you know, the resistance over the total is 4. And then I know the current is going to be, well, 12 divided by 4 equals 3 amps. 6 amps, 3 amps. These are going to add together to get to 9 amps at the end. And you could still pretty much solve all of this problem because of this information that we already know. The only thing that I think is important to realize is that, yeah, 12 volts gets dropped over the whole of this section, but that's broken up into 9 volts getting dropped here and 3 volts getting dropped here. How did I know that? Well, if I go V equals IR, I know the current through this section is 3 amps. Now the resistance of this is 3. 3 times 3 is 9 volts. Now, do you need to know all of this? No, you don't need to know all of this. I'm just showing you guys this. Again, don't stress if not many of this stuff made sense to you. All I wanted to show you guys is that 2 things. Those 2 things for this circuit are, hold on a second. Those 2 things for this circuit are, 1, you have the knowledge you could do this. So you actually have the requisite knowledge to do this, right? And the second one is that you can use effective resistance, to change circuits. So a 3 ohm and a 1 ohm resistor, that can be approximated with one big 4 ohm resistor. And then this just becomes a parallel circuit and you can do all your normal work with that. And the same thing would happen if you had a series circuit with a parallel section. You would just approximate that to a single resistor and find the effective resistance and then treat it like a series circuit. So it's actually not as difficult as you might think. We're going to leave this behind because I know that already people are like, I don't need to know this. Why are we spending so much time on it? So let's move on. This was the homework that I set, and you know what? I haven't set this as homework, and I'm not going to set this yet. I'm going to give you guys a little bit of a break today, so you don't have to do that. But I do want people to jump on it to Edroller later on today to give this a try. Now, a couple of points here. First point, if you find that I am doing a really bad job of explaining this, and you know what? I take no offense. I take absolutely no offense if you think that I'm doing a bad job. 1, this is the first time I've ever taught this. And 2, some people learn differently. But if you do learn differently, you still need to learn. So here are 2 links, and I can put these up later on in the Google Classroom, to a Khan Academy videos that go through the same sort of circuits that I went through on Tuesday. So if you really want to watch someone else do it, then sure. We've also got a Rollo, which he does a really good job of explaining the circuits as well when he goes through it. But remember, if you don't understand me, if you don't understand what I'm saying, you don't understand how I teach, don't sit there and be like, well, I'm a bad teacher, so therefore I'm going to get a bad mark on the test. No. If you don't understand what I'm saying, you need to take it onto your own hands and be like, all right, fine. I'll look up someone else. I'll look up a better teacher. And you might think that I would find that offensive. I actually don't find it offensive. Because what you'll do, I would make me really proud, because what you would do is you were saying, I'm looking for the teacher that explained things to me the best. And it's like, if you can find that, then good for you. I want to talk about now comparing the two types of circuits. Already we've talked about this, but just so we can re-explain this, a series circuit only has one path. It only has one way that the electrons can go around a circuit, whereas a parallel circuit has multiple paths. And the electrons can go down each of these lines in parallel. They can do it at the same time. And so because they can do it in the same time, that's why we refer to it as parallel. These lines in this graph are all straight, to sort of say these lines are all parallel. So I guess it sort of further affirms the idea of a parallel circuit. But yeah, just remember that all the parallel means is that there are multiple paths for it to flow through, not just one. Next up, so we've already done this, so that's why I'm going through this quite quickly. This is what it could look like in real life. In real life, you might have something. This is just the same sort of picture. All that we've got in this picture is just, different leads. Then remember, these light bulbs are considered just like normal resistors. So it doesn't matter which way you put those in. You can put them in forwards or backwards. As long as it's attached to negative or positive wire, it'll still conduct electricity. Now, I want to talk to you guys about these two circuits here. This is going to be the big comparison between the two. Let's pretend that these two resistors are, let's make it easy. Let's say this is 1 ohm, this is 1 ohm, this is 1 ohm, this is 1 ohm, and we'll say that this is 12 volts. Okay, really quickly, which one is the series circuit? The one on the left or the one on the right? Am I muting people? Which one's the series one? The one on the left or the one on the right? Series is on left, is what Rochung says. Does anyone agree with him? Someone does. Someone says, yep, it's on the left. Good. Brendan, excellent. So let's talk about this then. So this is the series circuit. This is the parallel circuit. And we're going to explore what makes these guys, what makes these guys tick. So we already know the basics, right? We already know that if the total resistance here is 2 ohms, so therefore we know that we're going to have 6 amps going through this circuit. Right? Whereas the total resistance of this one is going to be 1 plus 1 is going to be 1 over 1 plus 1 over 1 equals 1 over 2. It's going to be 1 over RT. So therefore, the total resistance of this is actually going to be the total resistance of this is actually going to be a half. So that means if I go, that means that the current through here is actually going to be 24 amps. Believe it or not. No. Yes, I'm right. 24 amps. Give me a sec. Yeah, because voltage divided, if you take, if you work it out, this should be 24 amps. Normally I don't do this much effort for these types of problems, but I think it's important to look at this. Now, if I was to then compare the voltage drops, right? This one's going to drop 12 volts, and this one is going to drop 12 volts because the current's going to split. The current's going to split, and we're going to get 12 amps going up and 12 amps going down. Whereas here, the current doesn't split. I end up with 3 volts getting dropped here and 3 volts getting dropped here. And so therefore, we can now sort of say, well, which of these is going to be brighter? Which of these light bulbs is going to be brighter? The ones in the series or the ones in the parallel? What do you guys think? Which one do you think is going to be brighter? Come on, guys. Rochung, what do you think? Which one's going to be brighter, the series or the parallel? All right, I got no answers here. The series is going to be brighter, is what Kelvin says. Does anyone agree with Kelvin? Alan says the parallel is going to be brighter. Let's, can I get someone up here to settle this tie between Arn and Kelvin? Which one's going to be brighter, series or parallel? Yvonne says parallel too. Well, the easy answer here, sorry. The easy answer here, hold on. Crap. Sorry. Pardon me, ladies and gents. I apologize. I had a bit of an issue. But yeah. So Phoenix says parallel because more volts. Okay. And Phoenix is not wrong. Phoenix is right. He's actually right for 2 reasons. But ultimately, yeah, the parallel circuit is going to have greater, is going to be brighter. The main reason it's going to be brighter is it's got a greater voltage drop. We've got 12 volts getting dropped across here compared to this guy over here where we've only got 3 volts. So that means these are going to be brighter. And let's actually just, for a second, let's just explore one extra little thing here. We now have the ability to look at the power of a circuit because, leading up to this point, we've never been able to do this. Like I've never been able to teach it to students until now. Power equals voltage times the current. So if I look at this top one, I've got 12 amps at 12 volts. I've got 144 watts getting dropped over this resistor here, this light bulb. And I've got 144 getting dropped here. And remember, watts is power is linked to energy per second. That's how much energy is getting dropped over here, 144 watts. Let's look at this one down here. This has 3 volts. Power equals voltage times current. This has 3 volts at 6 amps. 3 times 6 is 18 watts. Okay, so we can see straight away that there is a far less power getting dropped over this resistor per second. Now, the main way that we usually refer to this, and the main way we normally teach this is just based on voltage though. We can look at current, but we're not going to look at current too closely here. But the main one is to talk about voltage. The voltage here is this. More voltage gets dropped over here. And because more voltage gets dropped over each of these resistors, they are brighter. But the reason I'm showing you guys the other information about current is because I always used to get really confused. I used to be like, yeah, but won't this one have, you know, even though I'm like, won't these ones have more current, even though, and so won't that balance it out? Actually doesn't, because there are two splitting things. There's two ways to split this circuit. There is more available paths for the current to go through. So the current is larger. Look at that. The current is 24 amps compared to this one, which is 6 amps. And not only is the current greater, but it's also dropping more voltage. So that means we end up dropping more power. What does this look like? This looks like this. So because in these three globes, you know, we are sharing the resistor. Again, if this is a 12 volt, and this is dropping 3 volts, this is dropping this is a 12 volt battery. This is dropping 4 volts, this is dropping 4 volts, this is dropping 4 volts. If this is instead of parallel, then each of these is dropping 12 volts. So that makes sense that look, these bulbs would be brighter because they're each dropping 12 volts. And then I can always add, oh crap, that's out of time. Sorry, ladies and gents. The last question that I'm going to look at is this one here. This question here is a question that says, if I have two light bulbs are connected in series to a 9-volt battery, another 2 light bulbs are connected in parallel to a 9-volt battery, which bulbs are brighter and why? You know what? I'm going to make this today's homework question. So on top of it, Rollo, I'm going to make this the homework question. I'm going to put this on the Google Classroom right now. All I want you guys to do is to answer this. And this type of question would be worth 3 marks, because what I'm going to also get you guys to do is, I don't want you just to say which bulbs are brighter and why, but in that why section, I want you to talk about why are the circuits set up the way they are? How are they different? Remember that one of them shares the voltage, whereas one of them splits the current.
Now, Kirchhoff's second